This video continues our study of the use of calculus to describe motion of a particle in a straight line. In the previous video, we saw that if we started with the displacement x, then by differentiation with respect to time, we can obtain the velocity v, and v is simply dx by dt. And if we know the velocity v, then we can obtain the acceleration by a differentiation process again. So we've got the acceleration a is dv by dt. Now we know that integration is the reverse to differentiation. So if I wish to progress from the acceleration to the velocity, then I need to integrate. So this means that I can write v is the integral of a with respect to time. When I do this integration, I must remember that there will be a constant of integration involved in the answer, and I shall need to use some knowledge of the motion to find out what the value of that constant is. Similarly, if I want to move from velocity to displacement, then I'm going to have to integrate the velocity. So to move from velocity to displacement, I need to integrate. So I've got x is the integral of v, and again we've got the issue that there will be a constant of integration that needs to be found. So let's have a look at this in terms of a couple of examples. So for example 1, we've got a particle is moving along a straight line containing the point O. At time t seconds, the displacement of the particle from O is x meters, and the velocity of the particle is 0.36 t squared. When t equals 1, the displacement of the particle from O is 2 meters. Find the displacement of the particle from O and the acceleration of the particle when t equals 2. So in this case then, we know that we have got the velocity, and we know that if we want to move from the velocity to the displacement, we have to integrate. So we've got x is the integral of v. So in this case, x is the integral of 0.36 t squared, which gives me 0.1 t cubed plus the constant. To find the constant, I need to use the information that when t equals 1, the displacement of the particle from O is 2 meters. So when t equals 1, x equals 2, but my rule is telling me that x is 0.1 times t cubed plus c. So when t equals 1, x equals 2, I've got the little equation 2 must equal 0.12 times 1 cubed plus c, which tells me that c is 1.88. So the expression for the displacement is x equals 0.12 times t cubed plus 1.88, and when t equals 2, we've got x equals 0.12 times 2 cubed plus 1.88, so that is 2.84. So when t equals 2, the displacement is 2.84 meters from O. If we know what the velocity is, then we can find the acceleration by a differentiation process. So we've got a is dv by dt. We know that v is 0.36 t squared. So a is the derivative of 0.36 t squared, which is 0.36 times 2t, or 0.72 times t. Substituting t equals 2 in, I've got the acceleration then is 0.72 times by 2, which is 1.44 meters per second squared. Moving on to example 2, a particle moving along a straight line passes a fixed point O with a velocity of minus 5.4 meters per second. T seconds later, when it is x meters from O, its acceleration is 1.2 t meters per second squared. Find expressions for the velocity and displacement at time t. Describe the motion of the particle during the next 6 seconds, and find the average speed and the average velocity of the particle during the next 5 seconds. So, to move from acceleration to velocity, we know that the velocity is equal to the integral of the acceleration. So in this case, that is the velocity is the integral of 1.2t. 1.2t is going to integrate to give us 0.6 t squared. We must remember the constant though. We are told though that when t equals 0, the velocity is minus 5.4. So if I substitute that into the equation v equals 0.6 t squared plus c, I'm obtaining when t equals 0, minus 5.4 must be equal to 0.6 times 0 squared plus c. In other words, c must be equal to minus 5.4. So our expression for velocity is v equals 0.6 t squared minus 5.4. We also know that to obtain the displacement from the velocity, we need to integrate again. So we've got that x is the integral of v. So, in this case, we've got x is the integral of 0.6 t squared minus 5.4. 0.6 t squared integrates to give me 0.2 t cubed. 5.4 integrates to give me 5.4 t. So my integral of 0.6 t squared minus 5.4 is going to be 0.2 t cubed minus 5.4 t plus a constant. I'm going to call the constant k this time so I don't confuse it with the previous constant. We know that when t equals 0, the particle is at O. So we can say when t equals 0, x equals 0. So that gives me 0 equals 0.2 times 0 cubed minus 5.4 times 0 plus k. In other words, k must equal 0. So the expression for the displacement is x equals 0.2 t cubed minus 5.4 t plus nothing, and of course we can omit the plus nothing. Moving on to part 2 then. Describe the motion of the particle during the next 6 seconds. Well, we know when t equals 0, x is equal to 0. It's worthwhile finding out whether the particle changes direction at all. Well, the particle will change direction when v equals 0. If v equals 0, we've got 0.6 t squared minus 5.4 must equal 0. That gives me t squared equals 9. So it changes direction when t equals 3. We only want to consider values of t between 0 and 6. So we don't need t equals minus 3. When t equals 3, the value of x is 0.2 times 3 cubed minus 5.4 times 3, which gives me minus 10.8. So the initial part of the motion, we've got x equals 0 when t equals 0. When t equals 3, we've got x is minus 10.8. Now it's worth seeing whether the particle passes through O again. So we could say that it passes through O again when x equals 0. So when x equals 0, we've got the equation 0.2 t cubed minus 5.4 t must equal 0. And if we factor out 0.2 t, that's 0.2 t times t squared minus 27 equals 0. So the particle passes through naught when t equals 0, that's the start of the motion, or when t is the root of 27, which is somewhere just over 5 seconds into the motion. And final thing we're going to do is find out the final position of the particle. So the final position of the particle is when t equals 6. And when t equals 6, we've got x is 0.2 times 6 cubed minus 5.4 times 6, which gives me 10.8. So I can now produce a little diagram to show the motion of the particle for us. It starts at t equals 0, x is equal to 0. It then moves out to x equals minus 10.8 when t equals 3. It then changes direction and goes back through the point O when t equals root 27, and it ends up at x equals 10.8 when t equals 6. And that little diagram will now enable us to answer part 3 quickly and easily. So the average speed is the distance travelled divided by the time taken. The distance travelled during the 6 seconds, well, we've gone 10.8 meters to the left, and then we've gone 21.6 meters to the right, so we've gone a total of 32.4 meters. So the average speed is the distance travelled divided by the time taken, which is 32.4 divided by 6, which gives me 5.4 meters per second. The displacement during the 6 seconds is the final displacement minus the initial displacement. The final value of x is 10.8. The initial value of x was 0, so the displacement during the 6 seconds is 10.8. Take away 0, which is 10.8. So I have a displacement during the 6 seconds of 10.8 meters. So the average velocity is the displacement, or the change in displacement, divided by the time. Is 10.8 divided by 6, which is 1.8 meters per second. That concludes our second look at using calculus to describe motion.